is estimate the natural log of 3 using 3 methods. All right, we have 3 techniques. We can use linearization, we can use Newton's method, or we can use differentials. All right, linearization and Newton's method go hand in hand in that they have a similar structure in the early goings, but then they separate significantly after that in the approach, because obviously Newton's method, you're kicking over to a calculator and then you're never looking back. But we'll start with linearization. So if you needed to estimate something like the natural log of 3, we would need, it's not a page, it's a separate side example. We're going to go with linearization first. I need a function. Okay, so using really any function that would have a solution that would be equivalent to the natural log of 3 would get the job done. But what we can do is we could say f of x equals the natural log of x where x equals, bless you. This is the key ingredient with linearization. And this is something that you should have kind of gleaned from the activity. I'll pass those back later. But the idea is not to actually let x equal 3. That defeats the purpose. If that were the case, I'd just plug in a 3 in the natural log in the calculator and call it a day. What I want to do is I want to choose a nice convenient value for a natural log function that's close to the one in question. So I need a number that works really nicely with ln that's close to 3. Bearing in mind that sometimes numbers are represented with symbols, e. All right, e is approximately 2.718. That's pretty close to 3. I mean, it's not like ideal. I mean, if it was something like 2.99999, that would be great. But 2.718 is better than something like 1. I mean, 1 is convenient for natural log because natural log of 1 is 0. It's clean, but it's not as close to 3 as e is. All right, so in the linearization process, we take the derivative. We evaluate the original function and the derivative. All right, so the original function would be ln of e, which is equal to, very good. And then the other one, it's just 1 over e. There's really nothing to do there. Again, this is supposed to be an approximation technique. So if our answer is in symbolic form, there's nothing wrong with that. The one thing I don't want to do is kick over to a decimal form, because if I did that, then what's to stop me from going to the calculator to begin with and just type in the natural log of 3? It wouldn't make sense. So my linear approximation technique, I like using y, would be 1 over e x minus e plus 1. So now, since I'm looking for ln of 3, and we know that for values close to e, this line is a good approximation of f of x equals ln of x, meaning if I were to graph f of x equals ln of x and this function, for values close to x equals e, they would look indistinguishable from one another. All right, they'd have to be very close, but that's the whole point. All right, so I can evaluate my model here for an x value of 3. So 1 over e times 3 minus e plus 1. Anything you do after this is for the purpose of checking. I mean, you could distribute it in the hopes of cleaning it up a little bit, but without any kind of real expectation that that's going to happen. E is an irrational number, and when you're dealing with those, you're expecting funky decimals. But this is what I'm looking for. All right, so this should be an approximation of the natural log of 3. So ln of 3 should be this. All right, so let's see what this is. 1 over e, 3 minus e plus 1. All right, So not 100% accurate, but pretty close. Close is good enough in this case. That's the whole point. Right, so we have a symbolic expression that represents the approximation of the natural log of 3. And it did not involve us having to use a calculator at all. All right. So that's the linearization technique. If we wanted to use Newton's method, what we need is a function that we would find the zeros of. All right? The whole point behind Newton's method is to be able to find the zeros of a function. Right? We use the program to shorten up the process. But the idea is that through Newton's method, we should find the zeros of the function, and those zeros should be whatever it is that we're looking for. So to make a long story short, it's telling us that there should be some value x that's equal to the natural log of 3. All right, that's our starting point. And we did it with radicals, but we didn't really do too much together involving other types of functions. All right. So what I want to do is I want to get this into the appropriate form, which means everything over to one side. I want to write it as a function so I can set that function equal to 0. All right, so I'm going to convert it over into exponential form. All right, so that become e to the x equals 3, and then bring the 3 over. E to the x minus 3 equals 0. This would be my f of x. All right, so in terms of what you have to do from here on out, this ends up being the easier approach. So if you have a choice, and sometimes you will, you might opt for this one because if you can come up with the equation, then after that it's all calculator work. If it's a situation where you have a really hard time coming up with the equation, then you probably want to stay away from Newton's method. All right, so program Newt. I got my function, e to the x minus 3, so e to the minus initial guess. You know, like, that requires you to have some kind of sense of what the solution would be, unless you're taking a shot in the dark. And we I think know initial guess. We do know the dangers of taking a shot in the dark, because if there are multiple solutions, it might drag you to the wrong one. All right, but this is the natural log function, or at least what we started with. We're not expecting more than one intersection, so I'll put in a 10. I don't know. So 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 13 iterations, because I accidentally counted the repeated one. So I started with an initial guess of 10 for some reason. Initial guess of 10 with 13 iterations. And so we get the natural log of 3 is approximately equal to 86. All right, so the benefit of Newton's method is that you get a more accurate answer, because if I type in ln of 3, I get the same number. All right, so you're getting accuracy, but you're getting a lack of exactitude in that. And it's a weird thing to say, because it's like, well, isn't this more exact than that? Well, this is an exact expression, and there's no rounding at all. There's no funky decimals, nothing like that. This is the exact form of an approximation. All right, this is actually the approximate form of an exact value. So what's better? Well, it depends on what you need. All right, but this is closer to the true answer, because that one was around 1.10. Okay, so pros and cons to either, depending on what you're looking for. The last technique, this is like review all in one shot, is differentials. Or are differentials, I guess. I don't know. Grammar. All right, so with differentials, it could be complicated because, again, it requires you to have a sense of the function that you're working with. All right, so we'll go back to the technique that we used for linear approximation. We said that f of x is equal to the natural log of x. All right. So we don't really have much in the way of wiggle room here, or at least it doesn't seem like we do. So we're going to let x equal e, and then we'll just follow the approach. So we'll have f prime of x equals 1 over x, so that's the same as before. Now, another way to represent f prime of x would be dy dx. All right, the differential form of this differential equation has us taking this dx and swinging it to the other side. Yep. All right, so this is where it gets a little weird, but it's actually not that bad. It's just, it's not going to look really that nice in the final answer. But that dy represents your estimated value. Estimation, approximation means the same thing. All right, so estimated change. All right, I have the 1 over x. I know what x is going to be. The dx is the important piece. All right, that dx represents the deviation from your particular number. So what I'm looking for is we need, that's not a good looking need. Dx, all right. Specifically, we need to find the ln of 3, all right. So dx is going to be 3 minus whatever value you chose in your initial step, all right? Because that dx represents how far you're moving, how far you're deviating from the value in question, all right? So if I know that I need 3 and I chose e because it's convenient, then dx has to be the difference between the two. But I don't actually want to figure it out because if I do, then I have a funky decimal and that makes things troublesome, all right? So my answer is going to contain an expression involving e, and there's nothing wrong with that. So what I'm looking at here would be dy equals 1 over e times 3 minus e. All right. So in terms of brevity, this is probably the best. It happens the quickest. But you do sacrifice some accuracy. Sacrifice a lot of accuracy, right? So in that case, we're looking at, well, actually not that bad. It's about the same as the linear approximation. Yeah, because what this represents is the change in y, the estimated change from the natural log of e. All right, so if I were to find the ln of e, so at this point I would write ln of e, because that's my original function at the point. This represents the deviation from that. So plus 1 over e times 3 minus e. And so that's where you get your approximate 1.103 something, 104, all right. And so you're definitely sacrificing some accuracy, but it is, in terms of cleanliness, it's probably the quickest way to go. All right. So these are the 3 things that you would need to know. So if you work through the packet, those are the things that you're going to review.